recorded. It is recording. So everything is good. All right, so getting back to the homework assignment, let me pop up the homework assignment first, and we'll talk about it. Unless the majority of the class decides I don't want to talk about it. I don't want to know anything about a homework assignment. Then we'll skip it.
No, you should get to talk.
Yeah, I think so. All right. So this is the homework assignment. And the homework assignment is about a lotto game, and this is my own lotto game, which has a certain spin to it that the typical lotto game does not have, which is the combination or the permutation of the color balls. Okay. And I also want you to analyze this problem not only in terms of what are the chances of winning the jackpot, which is actually the easiest part of the whole homework assignment. I also want you to analyze, am I going to lose money or am I going to win money by selling these tickets? Okay, in other words, what are the chances that someone will win $10, $50, $1,000, $5,000, and $100,000? Okay, and not counting the jackpot, because the jackpot is not included in one of these. So what you need to do is to make the assumption that all possible tickets are sold, okay, and how much money am I going to make by selling all the tickets? And then you say, okay, because all the tickets are sold, so every single prize is going to be awarded, because there will be one person winning for each category of these particular prizes. So you have to kind of add up how many people will be winning $10, how many people will be winning $50, $1,000, $5,000, and $100,000. Okay, and then compare that with the amount of money that I would get by selling the tickets. Okay, so are there any questions about the setup of the question? In other words, about the rules of the game itself? There are no questions about the rules of the games? Not even the color balls, where only the permutation, the ordering is important, because there are only 3 balls, and I'm taking all 3 balls as the result of the ticket. So the combination is not going to be useful, because they're all going to be there. RGB will be there. The only question is, how are they ordered? So that's the only part that is kind of different from all of the other lotto games. All right. So what we'll do is we'll go ahead and analyze this problem. And we'll do it by paper, or we can just do it using a text editor first, and then we'll take a look at the problem. All right, so what you want to do is to kind of think about this problem after I draw the 6 lucky numbers and the 3 color balls. Okay, you want to think about this problem as, okay, now we have 6 lucky numbers, and then we have 24 not so lucky numbers. So you have to think about the partitioning of the numbers. Okay, so I'll just go ahead and write it down here. So this will be all recorded. So we have 6 lucky numbers and 24 not so lucky numbers. Is that okay so far? Now it is very important for you to understand that there are 24 not so lucky numbers, not to calculate the number of jackpot tickets, but the other ones. Okay, in order to find out how many people will get 5 out of 6 numbers matching and how many people will get 4 out of 6 numbers matching, you need to get the 24 not so lucky numbers, because they will make up 1 or 2 of the 6 numbers on the ticket. Are we doing okay so far? Yeah, just in terms of general ideas. Okay. All right. So now that we have this, we also want to understand how many color combination or permutations can we get? How many ways can we order 3 out of 3 items? There are 6 ways, because it's the permutation of choosing 3 out of 3 items. Okay. All right. So out of how do I draw 6 out of 30 items? Yep. Go ahead.
How do you draw 6 out of 30?
Well, how many ways can I draw 6 out of 30 items? And the ordering is not important. Go ahead.
If you draw 6 consecutive balls, removing 1 each time, you got 30 chances. There are 30 possible numbers on the first draw, 29 on the second,
right,
all the way down to 25 on the 6th draw. So that's
that is correct.
29 times 28 times 27 times 26.
And that number is otherwise known as the number of combinations, right? Okay, so that means, so the first thing you need to do is to find out the total number of possible tickets. Now, as a part of the homework assignment, I also wrote down here that I will only issue each ticket once, or each number will only be issued once. So I'm not going to issue like 1, 2, 3, 4, 5, 6 RGB many times. There will only be one ticket with that combination of numbers and that particular ordering of colors.
So you could have, in theory, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 6, 5. And if the winning numbers are 1, 2, 3, 4, 5, 6, you could still win the jackpot both times?
No, 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 6, 5 are considered the same because ordering is not important for the numbers.
Okay.
So there's only one ticket with the numbers 1, 2, 3, 4, 5, 6 because the ordering is not important.
Some of us were
Well, okay, with all the, with 6 combinations of the 6 permutations of the color.
Yeah.
Okay, so just to make it clear, if you just consider 1, 2, 3, 4, 5, 6 as the numbers on the ticket, okay, there will be 6 tickets with these numbers because there will be one ticket with this and then RGB as the color permutation, another one with RBG as a color combination. Yep.
Wouldn't there actually be 6 factorial?
It is 6
combinations?
No. It's
3 factorial.
It's only 3 factorial because we're choosing 3
Oh,
out
you're
of 3
talking
items.
just about the RGB.
Only about the
That
RGB
one
portion.
is 3 factorial,
Yep. So we have the next one is green. So GRB and then GVR, and then the last one is
yeah.
blue.
BRG and BGR.
BRG and BGR doesn't matter. Okay. So these are the 6 possible tickets with the same 6 numbers.
Yeah.
Okay. There won't be another ticket with 1, 2, 1, 3, 4, 5, 6. There won't be another ticket with that permutation of numbers. Because with the numbers, the ordering is not important.
Something else I wanted to clarify was we draw these tickets set, or we draw each ticket and then we draw balls. So each ticket is separately drawn from the balls, which means they have to be calculated separately. Yes. The chances of winning.
The chances of winning. Okay, let's take a look at the total number first because that will determine the probability of winning the jackpot. Is that okay? All right. Okay, so in terms of just the numbers, we have, the number of combinations is going to be choosing 6 out of 30 items. That will give you the number of combinations that we can get out of choosing 6 numbers out of 30. Is that okay? But that's not the number of tickets because out of each combination of numbers, I also have 6 ways of arranging the colors. So you have to remember to multiply this with the number of permutations of choosing 3 out of 3 colors. That will give you the total number of tickets. Now, the actual calculation part, I will leave it up to a spreadsheet, and that's why I told you guys you can use a spreadsheet to turn in because it's just easier that way. So if I go to a spreadsheet, and you can use Excel, I can open up Excel files as well. And go. All right, so we will calculate the total number of tickets. And that's going to be the combination of choosing 6 items out of 30 times the number of permutations of choosing 3 out of 3 items. And the correct number is that. Okay, is that okay so far? So I'll be issuing this many tickets. Are there any questions about this, or does anyone need clarification about how this number is calculated? No questions? This is all good? This is all good? Okay. So out of these many tickets, how many jackpots do we get? One is going to be a jackpot. So we say number of jackpot is going to be exactly 1. Now that 1 there are several ways to look at this 1 here. I know it is just 1 and 1 is 1, but why is it only 1? It's because once you partition the numbers into lucky numbers and not so lucky numbers, the jackpot means you have to pick 6 out of 6 of the lucky numbers. Okay, so that's the number of combination. What is the number of combination of picking 6 out of 6 items?
1.
Exactly 1. And there's only one color permutation that will match this one, and that's why it is just 1. Okay. Now, what if you want to win $100,000? Okay, so the $100,000 range is awarded to people down here. Anyone who has all 6 matching colors, matching numbers. So if you have 6 out of 6 lucky numbers, but somehow the color sequence is not matching, those people will get $100,000. And how many people are we talking about? Exactly 5, which is the permutation of choosing 3 out of 3 minus 1. Okay, because we have to take away the 1 that matches, because that one is the jackpot already. So going back to the spreadsheet, so the number of $100,000 awards, okay, so I'm going to put a pound sign here, pound, okay, is going to be 5, okay, is that okay? All right, so now we move on to the more tricky ones. The more tricky one is how many people will get 5 out of the 6 colors, 5 out of the 6 numbers matching. In other words, of the 6 lucky numbers, these people will pick exactly 5 out of the 6 lucky numbers and 1 out of the not so lucky numbers, right? So the number of combinations, or the number of tickets corresponding to choosing exactly 5 out of 6 is going to be the number of combinations of choosing 5 out of 6 times the number of choosing 1 out of 24. And then you have to multiply the number of permutations. So you still have to multiply that by 6 in order to get the total number of tickets with only 5 out of the 6 numbers matching, regardless of the color stuff. Is that okay? All right. So let's go ahead and take a look at what we are dealing with here. Okay. So we just want to calculate, match 5 out of 6 numbers. Okay. So we just want to look at the number of tickets that will fit this requirement. That is going to be the combination, the number of combinations of choosing 5 out of 6 of the lucky numbers times the number of combinations choosing 1 out of the 24 not so lucky numbers. And then times the number of permutations of choosing 3 out of 3 of the color balls. That would be the total number of tickets that will match 5 out of 6. Is that making any sense? Yep.
That's the confusing part for me. I think I did it that way anyway, but why is it multiplying?
Why is it multiplying? Okay,
Yeah.
so you can kind of think of the problem with a smaller one or a bigger one. It's all up to you. Okay, the first part is the combination of choosing 6 out of 5. I don't think anyone will have any question about this being a component of the total number of tickets that will have 5 out of 6 numbers matches, right? But this will only give you, just the number of combinations of choosing 5 out of 6 items. What about that missing slot? In other words, this will give you the number of choosing 1, 2, 3, 4, 5, 6 items. I said 5. So this will give you the number of combinations of choosing 5 out of 6 of the lucky numbers. But this guy here needs to be filled up. So if I know that there are this many ways to choose 5 numbers, 5 out of the 6 numbers, the 6th number still has possibilities, right? So I have to multiply this number by the number of combinations for this one position alone by itself, which is going to be the number of combinations of choosing one out of 24 of the not so lucky numbers. Is that okay? Because it's independent. The chances of picking these 5 numbers and the chances of picking this particular number, they are independent. There's no influence from one to the other. Is that okay?
Yeah.
Okay, so on top of all of these, you still have the RGB, the color balls, and there are always 6 permutations per number combination. And that's why we have to multiply by the number of permutations of choosing 3 out of 3 items. So now you have to take the product of all of these things to come up with that number. Is that okay? All right. So now that we know that there are exactly this many tickets that will be matching 5 out of 6 numbers, regardless of the color permutation, only one of these tickets, or let's see.
Still C is 5, 6 times C 1.
Say again?
I think it's easier if you do only for the number after that you multiply by 5 for the incorrect color and multiply by 1 for the correct color.
Up here you multiplied it by 6.
Yeah,
I guess what he's saying is
Oh, okay, I see.
multiplied by 1, then multiplied by.
Okay, gotcha. So basically, out of this, we have. Okay, let's look at the prize money. Okay, so if you look at the number of prizes of $5,000, so these are $5,000 items. It will just be.
1 to 6.
Well, I'm just going to redo the combination. So it'll be choosing 5 out of 6 times choosing 1 out of 24. And then the other ones will be the remaining portion, which will be the people getting $1,000. So the number of $1,000 prizes is going to be just this number minus that number. So there'll be 720 people getting a $1,000 reward. Yep.
Also, over here for a second, the 864 with the is
Say again?
So we didn't really need to do the match 5 out of 6. We could have just done the 5,000, 1,000 if we could have just skipped to those, right?
Say again?
We could have switched straight to the 5,000 and 1,000 calculation. And then instead of having to do the 864.
Oh, you don't have to do the 864. I just want to come up with a total number of people first, and then partition that into people who get the $5,000 prize and the people who will get the $1,000 prize.
Alright.
So you don't have to do it this way. You can just come up with 144 and 720, but you have to kind of show me why you think there'll be 144 people getting the $5,000 reward. All right, so with this out of the way, the other one is actually about the same. Okay, so if you think about the number of people who will be matching exactly 4 out of 6 numbers, the total number of tickets matching 4 out of 6 numbers is going to be the number of combinations of choosing 4 out of the 6 lucky numbers. But then you have to multiply that to the number of combinations of choosing 2 out of the 24 not so lucky numbers. Because in order to come up with the actual total number of tickets, you have to calculate how many people would be, or how many choices do we have for these 5 or 4 numbers, and how many choices do we have for the other 2 numbers. And the multiplication or the product of these becomes the number of possible number of combinations that will only have 4 out of the 6 numbers matching. And then on top of all of these, we'll have this number of permutations. This part is always the same because we only have 3 out of 3 color balls. So this will be the total number of people matching 4 out of 6 items, or 4 out of 6 numbers. Of these people, people who will be winning $50 will be the people who have the right color combination, the right color permutation. Yep.
What I did, instead of multiplying it by the permutation of 3 out of 3, I multiplied it by 5 because I figured
That would be fine.
if they didn't get the that works.
Yep, that would work too.
Because there's 5 ways they could get the
Correct.
balls wrong.
Yep. Yeah. So the way I do it here is just to show the total number of each category, and then we separate and say, okay, out of this category, out of the this many people will be matching the color permutation, and it will be these many people not matching the color combination permutation.
Okay.
So it works out the same way. You can just use 1 and 5. But the 5 is because of it is the permutation of choosing 3 out of 3 minus 1. So there's a reason why it's 5. Okay. So that will just be the number of combinations of choosing 4 out of 6 items times the combination of choosing 2 out of 24. And then the rest will get $5. I mean $10. So the number of people getting $10 is going to be this number minus this number. All right. So now that we have the actual number of people getting each category of the prices, what we need to do is to multiply the prize money by the number of people who will be getting that particular prize. If I make the spreadsheet a little bit wider, we can do all this math here. Okay, the jackpot is not included because the jackpot is basically just going to the whatever I have accrued over time. But the number of people who will be getting $100,000 is just going to be this number times $100,000. So I'll be spending $500,000 to reward to 5 people who get all the correct numbers but the wrong color permutation. And then of the people getting $5,000, it'll be 5,000 times 144. And then of the people who get $1,000, it'll be $1,000 times the number of people who will be getting that price. So that will be $720. I just picked the numbers just right? They all match up. And then the number of people getting, or the total money I have to spend to reward $50, it's going to be $50 times 4,140. And this is going to work out it will work out to be the same number because it is $10 times the number of people, like that. So this is basically a categorized list of how much money, how much I have to pay off for each class of prices. So the total of these is just going to be the mandatory expense that I have to do for all of the prices, not including the jackpot itself. And that number, I think, is less than what I will be getting. So that means not counting the jackpot, I'll still be making some money.
More than a million.
Sorry?
More than a million.
Yep. Not a whole lot, okay? Not a whole lot. Okay, because if I sell all the tickets, somebody's gonna win the jackpot, right? So I won't be making any money. But in the end, you can still claim that I'll still be making money out of this game. Are there any questions about this particular homework assignment? How many people thought about doing it this way? Partitioning the lucky numbers and the not so lucky numbers. That is the most crucial step. Okay, that's good. Okay. So how did you? What about the rest of the class? Yep.
The problem was that I didn't know how to use most of those equations properly, so all of the math was wrong.
Yep.
I ended up using, I think it's permutation, those things in the combination, but I tried dividing properly in order to fix that. I got the number of possible tickets right, but then everything else kind of tumbled out of control from what I could see.
Oh.
Yeah. I also showed my work a little too much compared to this.
You can show more work. I mean, that's always not going to be a problem. Yep.
For that one ticket that won the jackpot, isn't that up when they also get 100,000?
No, the jackpot is not just the jackpot is just getting the jackpot. So the question, or part of the question is, what are the chances of winning the jackpot? So the chances of winning the jackpot is 1 out of this many. So that will be the answer to that. All right. Are there any questions about this particular homework? No. Okay. Well, other than the color permutation, I think the calculation of how many people will be winning a particular number, I think you can find that in other types of lotto game rules and calculations. It's just the little permutation about the colors. That's the only thing that can kind of throw you off. Because that's not in any one of the other games.
How it's going to change if you return the ball in the basket again?
So after you draw each ball, you put it back into the basket. That will make it, okay, would the ordering still be important? The ordering is not important. Okay, so according to what you're saying is, after you draw a number, you would put it back into the basket, right? So that means you have 30 choices for the first number, you have 30 numbers for the second choice, second ball, and so on. So the total number of combinations, or the total number is going to be 30 to the power of 6, right? But out of this, okay, some will be considered the same. In other words, if you draw 1, 1, 1, 1, 1, 1, it doesn't matter how you do it, it will still be the same. So now the calculation gets a little bit more complicated because you have to factor in and basically make sure you don't double count all of those.
Just subtract the permutation of the numbers, right?
You can't just do that because it depends on how many of the numbers are the same.
No, I mean like if you get, for example, straight ones, you have to just take it out. Or, anytime you have a similarity that, for example, if you have 6 numbers, 6 factorial, if you take it out of the entire count, it should actually give you the number of the ones that doesn't have.
Well, let me think about this. Okay, this is just the raw number. Okay, when you draw, there are this many possibilities. But out of these possibilities, if the ordering of the numbers does not matter, then you have to. Okay, so 1, 1, 1, 1, 1, 1. There's only one way to get this. Okay, so this is not an issue. But when you look at 1, 1, 1, 2, 2, 2, there are many ways to get 1, 1, 1, 2, 2, 2 as a combination. Because you can draw 1, 2, 1, 2, 1, 2. You can draw 2, 1, 2, 1, 2, 1, and it will still be considered the same. So in this case, okay, let's just look at this particular combination. How many permutations can I get? How many unique permutations can I get out of this combination? Okay, so we'll go ahead and try to do something by hand first, and then we'll try to generalize. So we have 1, 1, 1, 2, 2, 2. We have 1, 1, 2, 2, 2, 1. Okay, and so on. So the question is, how many how many permutations can I get out of this? Because I have to combine all of those permutations into one single combination and make sure I don't double count anything. So this is the same thing as choosing. It's the same thing as choosing 3 out of 6, right? It's the same number of combinations as choosing 3 out of 6, because 3 items are the same and the other 3 are the different kind. So I'm just guessing here, but there are this many combinations of arranging 1 and 2s, 3 1s and 3 2s. I may be wrong here, but I'm just guessing it.
So if the permutation was important, you didn't have to worry about all this math, right? If it's a permutation one.
That is correct.
Okay.
If
You
the
had to
ordering
separate
is
the
important,
section.
then I don't have to combine all the permutations into combinations. Now, what makes this problem more complicated than the original problem is in the original problem, you're not putting the balls back into the cage to roll it again. So that makes it easier to deal with. We won't have duplicate cases like that with the original problem. But once you modify the problem to allow the same number to reappear, then we have little problems like this.
Thank you.
Yep. Well, I can think about this and give you an answer for sure next time, but I don't have I don't have an answer that I'm certain at this point. Yep. All right. Any other questions? Yep. Go ahead.
So how are permutations and combinations used in programming?
How are they used in programming? Well, they affect probabilities. Okay, in terms of discrete probability distribution, it is very useful. So anything that has a randomized process definitely has to do with combinations and permutations. Can someone name a particular game where it has a nature where you have to throw a dice?
That's the one.
D&D?
Hmm?
Any, well, you mean like a game on the
How about games where you do not have an opponent? Backgammon is one, right? Okay, backgammon is one of the games where you throw a dice. So if you want to figure out what is the best move at any particular time, understanding how the probabilities will be distributed is going to be helpful. Now that's actually a more complicated problem than just looking at this. Okay, the other things you can also look at would be observing. Okay, so if you observe coin tosses, okay, and you say, okay, out of 100 coin tosses, you observe 40 are heads up and 60s are tails. Okay, so now if I ask you a question of is that coin loaded? Okay, what is going to be your answer? There's always a chance, right? There's always a chance that coin is loaded. But what is the probability of that coin being loaded when you observe 40 out of 100 coin tosses is a heads up, as opposed to 30 out of 100, as opposed to 20 out of 100, 10 out of 100, or 0 out of 100. Now, if I toss a not loaded even coin 100 times, there's a very slight possibility that they will all end up with tails up. So you cannot say that for sure this coin is loaded because there's always a probability. The question is how much of a probability? What are the chances that it can happen?
Less than percent. Less than percent.
It's well, you can calculate, right? Because in the case of coin tosses, what is the total number of possibilities in terms of coin tosses? It's 100 out of 0. This is the number of combinations of having a no head and all tails. Is that okay? The next one is going to be what if I only have one tail and 99 heads? Well, that's 100 choose 1. And the next one is going to be 100 choose 2, and so on. If you add up all of these terms up to 100 choose 100, what do I get as a sum? The summation is going to be, come on, you guys know the answer. We have 100 bits, okay? Out of 100 bits, how many ways can I arrange things? It's 2 to the power of 100. So now you can say, okay, if with a loaded coin, okay, okay, these are the number of combinations, but then you also have to multiply this with p to the power of 0, and then 1 minus p to the power of 100. This is the exact opportunity that you will get, no head and all tails. P being the probability of getting a head up with a particular coin. Is that okay? Sort of? No? Okay. Let's think about it again. Alright. So let's not think about 100 because 100 is a lot of things to draw on the board. Let's think about 4. Okay, so we have 4 coin toss events. Okay, and let's just say that I have a coin that may be loaded. So here's a coin that may be loaded, and so I have P as a probability of heads up, and I have 1 minus P of getting a tail. Is that okay? So for every single toss event, okay, I have P, which is going to be a number from 0 to 1, and that's the probability of getting a head up for that one single toss. Now, because the only other choice is to have a tail up, it has to be 1 minus P. That's the other choice. Is that okay? All right. If I want to have 2 heads and 2 tails, how many ways can I arrange your 2 heads and 2 tails? Or choose 2, right? There are this many ways to end up with 2 heads and 2 tails out of 4 different tosses. But out of these, for each individual event, I have P squared of a chance to get 2 heads, and then 1 minus P, the whole thing squared, of a chance to get 2 tails. So when you multiply this number by this number, that will give you the probability of getting 2 head and 2 tail out of 4 coin tosses. Is that okay? This is actually a part of the notes. It's already written. Yep. So, but to answer your question, this type of thing is useful for analyzing probabilities. And the ability to analyze, what are the chances that a particular point is loaded or something like that is really helpful because that's statistics. Now, statistics is a little bit different because in statistics, what you're doing is you're sampling a true population. Whereas in this case, you know the actual true population, but the theoretical part or the hypothesis has to do with what are the chances that this is the actual probability, and you can do the calculations this way.
So why are you multiplying it by and 1 minus P?
Because for each event, I have P chance of getting a heads up, and I have 1 minus P chance of getting a tail up. So to get 2 head and 2 tail, this is the actual possibility out of each sequence of 4 coin tosses. But there are this many ways to arrange 2 heads and 2 tails, and that's why I have to multiply the number of combinations of choosing 2 out of 4 items. Because I can choose any 2 out of these 4 slots to be heads, and then the other 2 slots will be tails. So that really also helped to answer this particular question. Choosing 3 out of 6 is the correct answer to that question. So to your question of, what if you put the balls back into the cage to roll again, we'll basically have to make sure that we take care of all of these cases. And it's going to make the problem quite a bit more complicated, actually. So you have a longer series of numbers in order to calculate just the number of tickets that I can issue. Are there any questions, out of this? No? Okay. Yep.
So if you calculated the combination of getting 6 out of 24, it would be exactly the same as the amount that you get from subtracting the total of your tickets minus the amount of money.
Is that with the modification that you mentioned or not?
No, just
okay.
The old question you made.
The old question, and then your statement was. Can you repeat your statement?
Can you just calculate the combination of getting 6 out of 24 to figure out if it's if it's profitable or not?
because then you'll be picking 6 out of
You know how much
24
money you don't
unlucky
have to
numbers,
allocate
right?
now.
So out of the not so lucky numbers, what are the chances that someone will pick, all unlucky numbers? Basically, that's
Well,
what you're
That's
calculating.
going to be the leftover, whatever you have left. It's gonna
That
be
is
the-
correct. That is the leftover. Yep. But that's not going to be enough because you still need to calculate, because if I change the prize money, that will shift, whether it is profitable or not. Is that making any sense?
No, I mean, like, if you calculate the 6 out of 24, it's gonna show
Yep.
you that the range that the numbers are wrong,
Yes.
it's gonna get covered altogether, right?
Correct.
So you don't have to really worry about multiplying anything.
But that will only tell me, how much money I'll be making out of tickets that will not be rewarded any prizes, right? And that's not all either, because what if someone has 3 out of 6 matching numbers? That's not going to be included in choosing 6 out of the 24 not so lucky numbers. Because, according to the rules of the game, if you only get 3 out of 6 of the lucky numbers, you don't get any prizes. But if you only calculate choosing 6 out of the 24 not so lucky numbers, that combination is not included.
Oh.
So that's not quite enough to finish the analysis. Yep.
If you were to actually use a coin toss those to 50%, can you tell us what that would actually be if,
This?
for the actual chance?
For the actual chance?
Yeah, for the actual chance for that, it's just a coin toss, so 50% chance.
It depends on what P is, right? Because if you have a loaded coin and P is 0.6, then it's different from a even coin where P is 0.5. So it all depends. Now, given a even coin, okay, 4 choose 2 is what? It's 4 times 3 divided by 2, which is 6, right? So this would be 6 times 0.5 to the power of 4, because P is 0.5, 1 minus P is also 0.5. So this would be the probability of getting 2 heads and 2 tails exactly out of 4 coin tosses. So that amounts to what?
0.375.
0.275?
0.375.
375? Okay. Which is actually the peak, if you look at the probabilities of getting any other type of combinations, they're all going to be lower. And that makes sense, because if you have a coin that is not loaded, that's even, getting 2 heads and 2 tails should have the highest probability. Okay. Any other questions? But I think the original question was, why is this useful in computer science? Right? That was the original question. Computer science a lot of times is not useful all by itself. It is sometimes a program is used to assess, okay, what if I have a theory that this coin is loaded? Okay, what is the probability of that coin being loaded? That would be one of the things you can do with probability distribution. The other thing is, what if you have one way to observe? Let's say you observe a game. Okay, you observe a game, and you figure out, okay, given a particular situation, a particular gamer has a 0.4 chance of doing this, making a decision to do something like this, and a 0.6 chance of doing something else. Okay, so you collect all of these statistics. Now, if you want to make an AI engine to counter the move of this particular player, knowing the probability distribution of what a player might do in a certain situation can help your AI to determine what is the best way to counter it. Is that making any sense? So that is one way to also utilize the probability, is to make a better video game, to make the AI adapt to a particular user or particular gamer by collecting statistical information about the habits of that particular person. Any other questions? Nope. Strategy?
I can have another example.
Okay, go ahead.
Games that involve combat actually require it requires the game to know what's a chance of someone hitting or missing, and then how often can that happen, and then when is it going to miss, when's it not going to miss. when's it going to be a critical, stuff like that. Like the entire battle system for most games requires a crap ton of math. Like, ridiculous.
It's modeling, right? Because they're trying to model the probabilities of an actual or virtual, okay, game. How many people play games like Call of Duty? Okay. Now, in the game of Call of Duty, does it do it by chance, or does it always have a? Is it deterministic or is it stochastic? That's what I'm asking.
The older versions were definitely stochastic.
Stochastic. So you can basically spray, and then there's a certain chance of hitting something.
Hitboxes, yeah.
The hitbox. Well, hitboxes is just the size of the thing, but the actual quote unquote virtual points where your weapon will land a shot, that's probabilistic.
Probably, yeah.
Right?
It's definitely different by weapon, of course.
Sorry?
It's different by weapon.
It's different by weapon, so that means it has to be there's a probability distribution, and it's different for each weapon. It makes sense, right? Because that's also true in reality. If you use a shotgun, then you have a certain type of spray pattern, and that's also distribution of probability.
Physics engines.
Physics engines can be useful. Well, can utilize probabilities.
I'm not asking questions.
Oh, okay. All right. So any other questions related to the lotto game, or just in general the distribution of probability?
Can you upload your source sheet?
You mean this one?
Yeah.
Save it.
So I have to do it and like look at it.
Okay. Just remind me to upload it at the end of the class.
You'll forget, so will I.
Well, it's saved on the on the actual drive.
Oh, there.
Yep. So we know we're not going to miss this one. All right. So with this out of the way, I'm going to do something. Just looking at the time here, we already started on the induction topic, and it has quite a few things inside. And
You say you want to go over a sample test.
well, I want to go over the sample test, but I need to go over these topics first. Discrete, recursion. There we go. Okay, so I want to show you guys a few things first. We'll skip Master Theorem for the time being, okay? So we're going to skip that one. And what I want to do is to talk about, how do you turn something that's well known to be iterative, how do you turn it into a recursive algorithm, okay? And out of the recursive options, how do you turn it into a way that it will match the Master Theorem template, okay? So that's what we'll talk about today, is that, okay? So it has to do with making an algorithm match or fit the Master Theorem template. So we'll start with something that is relatively simple, which is the linear search algorithm. So there's nothing magical about this. This is really simple and brute force, okay? I give you an array of items, and then the items are not sorted. In this case, it's an array of integers, okay? Just compare the integers. Parameter A is the array, parameter N is the number of items in the array, and parameter K is the value that I'm searching for. Are there any questions about the parameters? Okay. So, given these parameters, I would use a local variable I, initialize local variable I to 0, basically to start from the beginning of the entire array. I stay in the loop as long as this condition is true. In other words, I stay in the loop as long as 1, I have not reached the end of the entire array yet. So I is less than n, and I have not found the item that I'm supposed to be finding. So those are the reasons why I would stay in the loop. In other words, the reason to get out of the loop is 1, I have looked through the entire array and the item that I'm trying to search for is not in the array. That's one way I should get out of the loop. The second reason to get out of the loop is saying, hey, it's here. The item or the value that I'm searching for, K, is right here. It's time to get out of the loop. I don't need to count the number of items matching K. I just need to know whether there is one or not. Okay? Are there any questions about the algorithm? Okay, for each iteration, I don't even need anything to do for the for loop. I just need a post operation of plus plus I to increment the index so that I will be ready to compare the next item. The return is just returning whether I is less than n or not. Because if I is still less than n by the time I exit the loop, it means I have found an item matching k. If I, on the other hand, equals to n, that means I have not found anything that matches k. Okay, so that's how this algorithm works. Is that recursive? It's not recursive. So if it's not recursive, the master theorem cannot be used to analyze the complexity of this algorithm. Okay? Because what I want to do is to use the master's theorem to analyze the time complexity of any algorithm. So this is not going to work. Okay? This is our first try to turn it into a recursive subroutine. So the recursive subroutine version says, okay, instead of using a loop, I'm going to use a conditional statement and recursion. And it will separate the incoming cases into two separate cases. The base case is, oh, if the array has nothing in it, okay, there are 0 elements in the array, then whatever I'm trying to search for definitely cannot be in that array, kind of by definition. Is that making any sense? Okay. If you ask me and say, oh, Tech, can you tell me whether 5 is in this array or not? But that array is empty, what do you think my answer should be? No. No, it's not, right? Okay. So that makes sense. What if n is not 0? What if n is greater than 0? Well, then what I'll do is to say, well, let me take a look. Oh, okay, I made a mistake here. This should be just, 0, okay? In other words, I'm just looking at the first item. Let me change that first before I forget, because I don't want this to be wrong. When I type this in, I have to type it in raw HTML code. That's why it doesn't look very friendly. There you go. That should do it. Okay, that's good. Okay, so this is the lazy way of doing recursion because if n is not 0, in other words, there's at least one element in the array A, my only job is to look at the beginning of the entire array and say, well, let me check the first item of the array. If it is k, then I'll just say, okay, we are done. Because in C and C++, the logical OR operator is using the lazy evaluation, which is also known as short-circuited evaluation. If the left-hand side of the double bar or the logical OR is true, it does not bother to evaluate the other side, which is great, okay? But what if the first item of the array is not k? What if this is false? Well, I'm lazy, right? I don't want to search the rest of the array. I'm going to tell someone else to do it. So what I'll do is I'm going to call search again. This time I will pass a plus 1 to a and n minus 1 to n. Okay? In other words, I look at the second element and up of the entire array and say, this is the beginning of an array, okay? And I pass it to another invocation of search to get this job done. And is that okay so far? Okay. So are you convinced that this code will work? Okay. It is recursive. It does not have a, go ahead.
If it's short circuit, wouldn't it just return 0 or false?
No, because if short circuit, it means if it can determine the actual answer for sure, then it won't go any further.
Yeah.
Now, with a logical OR, if the left-hand side is false, then you have to evaluate the right-hand side, because if the left-hand side is false but the right-hand side is true, then the entire disjunction is still true. So that's why when a bracket 0 equals to k is false, it will force the program to call search again recursively. And your question is? Okay, all right. Is that okay so far? Well, this is a recursive version, which is good. unfortunately, this does not fit into the pattern of the Master Theorem either, okay? Because the Master Theorem wants you to have an algorithm that breaks a big problem into equal chunks. And in this case, it's not an equal chunk. It is one size smaller than what it was. It's not 1/2 or 1/3 of the original problem. It's not a proportion of the original problem. Is that okay so far? Okay, so it doesn't fit the requirement of a Master Theorem template. Yep.
For the for loop, you had the pre-increment. Does it matter in that case whether you pre-increment?
Does not matter.
Okay.
Okay, the question was, does it matter whether this is pre-incrementing or post-incrementing? And the answer is it does not matter, because as an expression, plus plus I, the value of plus plus I is not utilized by anyone else. So whether you do a plus plus I or I plus plus really does not make any change. That does not matter, because no one is actually using the value of the expression. It's only the side effect of the expression of incrementing I by 1 that is useful in this case. All right, so here's the last version of search, okay? So this is another recursive version of search, but in this case, it is a little bit, oh, this is bad. I made a mistake here. Because there's no way it can actually confirm whether an element is in the array or not. Well, because there's no comparison of any array element to k. So this will basically return false all the time. Okay, it's not gonna work. My mistake here. It will end, but it won't give you an answer. So with this one, I will have to make a change. Okay, let me make that change first, and then we'll go back and fix this one. Okay, when it's 1, I'm just going to indicate whether a bracket 0 is k or not. Okay, now it's going to work.
What happens when you do this late at night? So what happens when you do this late at night?
Oh, this is not going to work either. Because what if n is 0? Then it will try to do the recursion again.
I didn't see what you did.
One more change. If it's 1, then I will compare the only element. And there's another else if here. If else if n is greater than 1, we'll do this. I can't just do this because I have to do it in the raw HTML code.
So you need a line breaks.
No, it's a Moodle thing. There we go. There we go. All right, so this one will work. Okay, so we have 2 base cases here. The first base case is when n equals to 1, if I give you an array with only 1 element, the answer of whether that element matches k or not is easy to answer. I just compare the first element, which is the only element in this array, with k, and whatever the answer is the right answer. The other base case is the else statement here. How do I end up with this particular else statement? The 2 conditions both have to be false, right? So that means n equals to 1 has to be false. But n is greater than 1 also has to be false. What does that mean when n is not 1 and it is not greater than 1? Well,
Less than
0. Okay?
Just less than 1.
Or 0 or less than 0. Less than or equal to 0. So in that case, I have an array that has no element, and obviously k cannot be a part of that array.
But in this case, it's just n is less than 1. Because you have the 2 conditions you have is n equals 1 or
Correct.
n is greater than 1.
Yep. Okay, so the only part where it will do any type of recursion is the array is not it has more than one element. So in that case, I split it into two cases. In the first case, I say, well, let's start at the same point, but the size is half. Okay, so you take care of the left half, and then the other one will take care of the right half. So this one will take care of the right half, and you can see how I start the array with this particular recursive call. I use n divided by 2 to add to a, and that's how I can specify the second half of the entire array. But in this case, the size of the array is going to be n minus n divided by 2, because n divided by 2 elements is already handled by the left-hand side, so this one only has to handle n minus n divided by 2 many items. Okay, so basically for each recursion, I chop it down into two halves, and each half is about the same size. They may not be exactly the same size. It all depends on what n is. If n is an odd number, they'll be off by one element.
That would be just a double comparison of the middle element. The middle element, so the second element.
No, the middle element will not be compared in both of them. It will only be compared in one. Because the range of the left-hand side and the range of the right-hand side in terms of the recursive call to search, they do not overlap at all. Okay. So this turns out to be a format that will fit into the Master Theorem template, and as a result, we can use the Master Theorem to analyze the time complexity of this particular recursive algorithm. Okay. Are there any questions about how all three algorithms are basically the same thing? They're basically all doing quote-unquote linear search. Any questions about the algorithms themselves? Yep.
Is this assuming that k is, like the value of k is in a somewhere, has to be found in a somewhere?
I want to find out whether that is the case or not. So I'm searching for the value k in the array A. If k is in A, I want it to return a non-zero. If it is not, I want it to return 0. Are there any questions about this? No questions? Okay. So what we'll do next is to go back and take a look at the Master Theorem. This is also a new topic. We have not talked about this before the break. There are two links here. The first one goes to the Wikipedia page, and the second one goes to my kind of condensed format of the Master Theorem. Okay, so the whole point of the Master Theorem is the time complexity of an algorithm is 1, it is a recursive algorithm, and 2, the time it takes to solve a case of size n is determined by this little equation here. So I'll just go ahead and explain what each term is. N divided by b, okay, this term here, is the size of each subproblem. In other words, you're breaking a big problem of size n into subproblems, and each subproblem has a size of n divided by b. In the case of binary search, b is 2, okay, because you're dividing the entire array into two halves, and each half is n divided by 2. In the modified search algorithm, the linear search algorithm that we just talked about, b is also 2 because I'm breaking up into two halves. A is determining how many times do we have to solve a subproblem. In the case of binary search, A is just 1. Because once we do one single comparison in binary search, we only have one half of the array remaining that can possibly have the value that we are searching for. So A is 1 in the case of binary search. In the case of linear search, A is not 1, because what if the first half does not contain the value that we are searching for? Then we have to go for the second half. So A is 2, same as B in the modified version of linear search. F of n is basically the time complexity of searching, well, not searching. It's the time complexity, or the amount of time that is taken by the algorithm, but not including the recursive calls. So excluding all the recursive calls, how much time do we have to spend for each invocation of the algorithm in order to solve the problem. That's f of n. In the case of binary search, f of n is a constant. It does not depend on n. In the case of the modified search algorithm, f of n is also a constant because it is a constant time to do a single comparison or a series of comparison. Are we doing okay so far with this notation? Let's go back to binary search and let's take a look at binary search.
I think you had a question there.
Oh, sorry.
The guy in the picture.
Go ahead.
You had a question.
Oh, okay.
So wait, what does A stand for again?
A is the number of subproblems.
So why is it 1 for binary search?
Because in binary search, the number of times you have to do the recursion is only once. Think about binary search. What does it do?
Cuts it in half.
It cuts it in half. Now, what do you do with? Okay. This is not working. So let's say this is the entire array that you are given. Okay. So with binary search, what you do is you pick a midpoint and you compare to whatever is right at the middle of the entire array. Out of this comparison, there are 3 possible outcomes. One is this is the item that you're looking for, you got it. The other outcome is this is greater than the value that you're searching for, so you can basically toss away this half. And then the third one is this is greater than the value that you're searching for, and you can toss away this half. Is that okay? So you have only 1/2 remaining for the recursive call to handle, and that's why A is 1 in that case.
So would the same be for the merge sort?
For merge sort, it will be different because for merge sort, you're basically breaking into 2 halves, and you say one recursive call will handle this half, the other recursive call will handle the other half. But when you have the 2 halves back from the recursive calls, then you have to merge those 2 into 1. So that's why with merge sort, A is 2, B is also 2. But f of n in the case of merge sort is n itself. It's like some kind of constant times n, because the merge process will take an amount of time that is proportional to n itself. Okay. Any other questions about this particular equation? It has to do with the structure of the recursive algorithm. Is that okay so far? Okay. So once you know what is A, what is B, and f of n, we have 3 possible cases. Okay, we're going to skip this part here. The 3 possible cases is, first of all, you can define f of n to be big O of n to the power of some number c, and you also have to constrain c to be less than the log with b as a base of a. Okay? All right, so let's take a look at this one and find out, okay, can we find any cases like this? I think we have one case like this. What do you guys think? Okay, so let's take a look at this again. Okay, one more time. This means f of n, which is the amount of time it takes for each level of recursion to take place, but not counting the recursive calls themselves, is going to be determined as a power of n, which is the size of the problem. But the power itself, which is c, is going to be less than the log of a using b as a base. Okay? Think about the linear search algorithm, the modified linear search algorithm. So what I'll do is I'm going to pop that page up as a separate tab, and then we'll take a look at that. Okay, let's take a look at this algorithm. What is A in this case? 2. A is 2, right? Because it is possible that I have to go for the left recursive call, it doesn't find the element, and then we have to go for the right recursive call. In other words, if k is not in the array, go for 2 recursive calls. That means A equals to 2. Does that make any sense? What is the divisor of the problem when I chop it down into smaller problems? It's kind of spelled out here. What is B? B is 2. Why do I know it's 2? Divided by 2. And this one is kind of divided by 2, but I take care of the odd number using this method. Okay, so if A is 2 and B is 2, what is the log of A using B as a base?
Log 2 of 2
Log
is
2 of 2 is 1. Yep. Okay, cool. What is the amount of time that it takes, not counting the recursive call? How much time do I have to do the comparisons? And also the overhead of calling, setting up the parameters, and returning. In other words, how much time do I have to spend to do something like this, the disjunction here, and also the return statement, or each individual return statement? Constant. It's a constant time. Okay, it does not depend on the number of elements in the array. Okay, so that means in this case we also know. Where did I write here? Okay, so in this case we know that A is B, which is 2. We also know that the time complexity of case n is some kind of constant, right? If it is some kind of constant, it is big O of 1.
Why do we know it's a constant? Why do we know it's a constant?
Because it does not depend on n at all.
Oh, okay. That's what you mean.
Okay, so n can be a really huge number. Let's say 1024. Okay, if n is 1024, how much time does it take to compare 1024 to 1?
1 unit of time.
1 unit of time. Doesn't matter what n is, right? How much time does it take to compare to 1 or greater than? Constant time. How much time does it return? Does it take to return? That's not dependent on n at all, right? The OR operator does not depend on n, and that's why together it is a constant time.
I see.
Okay. Now, if it's a constant time, it is also known as big O of 1, because we can always find a constant to multiply to 1 to get to f of n. But what is 1? If I want to re-express 1, so that it is a power of n, how would I do it? N to the power of 0. Okay. So that means C is 0.
Which means that log 2 of 2.
Yep. So if I go back to the first tab here, yep, you got it. So that means all of these requirements are met, because I can express the amount of time not counting the recursive calls, okay, as f of n is just a constant time, which is big O of n to the power of 0. C is 0. 0 is less than 1, right? Because we get the 1 from log B of A. Is that okay? So it's meeting both of these requirements. Once these two requirements are satisfied, then we can express the actual time complexity to be big theta of n to the power of log BA. Tell me again, what is B? B is 2. What is A? 2. Log 2 of 2 is 1. N to the power of 1 is n. It's a linear, the amount of time it takes for that algorithm to complete is proportional to the size of the problem, linear. Is that surprising? Nope. It's a modified form of linear search. So in this case, I am taking a well-known simple algorithm that is iterative and turn it into not just recursive, but into a recursive form that fits into the template of the Master Theorem, so that I can apply the Master Theorem to analyze the time complexity of the algorithm. Let's take a look at the second case. The second case is actually more well known than the first one. There are more algorithms fitting the second criteria. Okay, so let's take a look at this one here. This will be the last thing we do today. Okay, f of n is, this thing here. Now you can see that c can be a very small number, can be 0 as well. And this k is basically asking how many times are we applying log to n. The base is not important, but how many times are we applying log? K can be 0, which means we are not applying even once of the log function on n. Okay. If you take a look at binary search, let's find out what these numbers are. So let me take a look at this one here. Okay. And we'll say for binary search, how much time does it take for each level of function call to complete for binary search in the recursive way? It's constant time, right? Yeah. So f of n is some kind of constant k, which is big theta of 1. Great. How do we express 1 using n to the power of c of log k of n?
Well, you'd express it as n to the 0 log, or n to the 0 log to the 0 of n. Wouldn't you?
Well, the first thing is to take care of c. C can be 0, right?
C can be 0.
Okay, so we will say c equals to 0. And what about the number of times we apply log?
Well,
It will be 0 times.
We know that c equals log BA. If log BA is 0,
Yep, I take it back. This.
work?
Well, I know binary search fits in this pattern because it's right here. Okay, A is 1, B is 2, because we break the big problem into equal halves, but only one half needs to be solved. So that's why A is 1 and B is 2. When B is 2 and A is 1, what is log 2 of 1? Log 2 of 1 is?
0.
0, very good. So that's how we determine C is 0. So we apply the C being 0 here, K being 0 here, which means we are not applying log to n even once. So we should get big O of n and not log of n.
Yeah, no, it's log of k plus 1.
Log of
t n is log k plus 1.
Oh, that's the, okay.
So you got like n of n and n. That's
Right. Well, that's the final algorithm, complexity.
So k is 0 here.
But at each level, k is 0. So log, okay, you apply 0 times of log on n, you get 1. You get a constant, right? Okay. So that's how we fit into this category, and then that's how we solve for the time complexity. Yep. I was hoping that I would be able to get to the practice test today, as if I could not in the next Thursday. The exam is going to be next Thursday. The practice test is going to be this Thursday.
Reminding me. You said you the last one? Yeah, I think the last class. Yes. I do.
It was 50 points. The other two were 30.
Yeah.
YouTube.
I forgot to multiply in the homework for the total number of winners. I forgot to multiply those last two numbers that he did. I can't remember the.
Did you change the spreadsheet from the one that
No.
you were doing?
Oh no, I pretty much had exactly what I had before, so I just made it prettier.
But you didn't account for the people who lost.
Yeah. I think I basically did exactly like I forgot to add that part in because I remember.
Upload that file for me.
Oh, yeah, sure. I'll try to. I won't remember necessarily, but actually, I'll tell them after class. All right, later, Chris.
Oh yeah, that's like the what was it before that? Metro.
Exactly.
Yeah, but I forgot to count, like, for, like you said, basically, before spring break, to count for the number of, what's it called,
You at least counted for the